Good morning, students. Today we will see the mechanical properties and deformation mechanisms, Unit 5 for the subject engineering materials and metallurgy. So this is the syllabus for the Unit 5. So we will discuss about the mechanisms of plastic deformation, slip and twinning. So the types of fracture with the materials, and then the testing of materials under tension, compression, and shear loads, and then the three hardness tests, namely Brinell, Vickers, and Rockwell, and then the two impact tests, ISO and Charpy, and also the failure mechanisms of fatigue and creep. So, so many materials, when in service, are subject to forces or loads, as we know already. So we are using the engineering materials to perform some action or to do some thing in service. So while the materials are put in service, they are subject to loads or forces. For example, you can see that the aeroplane wing, which is made up of aluminium, the material aluminium, metal aluminium, and the automobile axle, so it's made up of steel, that is alloy of iron and carbon. So these two materials were subject to forces when they were in service. So while the aeroplane or when it is flying, so it will be activated to do some actions, and also the automobile axle is subjected to some force while driving. So how these forces or loads reacts with the metal or the material. So what will happen to their property? So that's the thing what we are going to discuss. So the mechanical properties, which is called, and how to predict the mechanical properties to avoid the damage to the above said structures when it is in service. So as I told us, we need to know the properties, that is the characteristics of the material. So you can see this is the diagram. So you can see that the photograph. So the axle, the steel axle in an automobile is broken. So because of the excess load or force acted on the axle while driving. So we have to design the member. So from which it is made. So the resulting deformation will not be excessive and fracture will not occur. So this is an unprecedented situation. So this situation would not occur. So when it is in service. So for that we need to know the characteristics of that material which are subjected to loads or forces. So this mechanical behavior of a material so reflects the relationship between its response or deformation to an applied load or force. So by knowing this mechanical material, so we can conclude that material will how the material will react to the subjected load or force. So there are many mechanical properties associated with any material. So the important mechanical properties are strength, hardness, ductility, and stiffness. So, how the mechanical properties are ascertained? So, we have to do some laboratory experiments which will replicate as nearly as possible. So, not accurately, but it replicate the situations as nearly as possible, the service conditions in a lab. So, from that experiment inference, we can come to a conclusion that this could be the characteristic of the material subject to that performed load. So, so what are the factors to be included while doing those laboratory experiments? The nature of the applied load, how the load is applied, and then how long it is applied, that is its duration, and then the environmental conditions such as the temperature, the pressure, or light, even the wind. So likewise, so these environmental conditions also a role in that laboratory conditions. So what about the load? How the loads are classified, or how the loads were acted on a material. So the load could be a tensile one or a compressive one, or it may be a shear one. So the magnitude of the load, so may be constant with time, or it may fluctuate, that it may vary continuously. So you can see that diagram. So the tension, the load which is in tension, the second one shows the load which is in compression, You see the arrow marks, and then the shear load, and then bending load, and then torsion load. So these are some types of load could be acting on a member. So regarding the application of time, so the load may be only a fraction of a second. So the load may act only a fraction of a second, or it may extend over a period of time. That is called, it may be of years. It may be a fraction of second, or it may be a number of years. And then the service temperature, as I told, the service temperature, whether it is room temperature or excess of the room temperature or sub-zero temperature, that plays an important role in deciding the characteristic of any material under force. You can see this diagram. So when a load is acting on a member, um, so the two types of forces are created. That is, on the top layer you can see that compression force, and then the bottom layer you can see that tension force. So we need to know the stress and strain, which are the characteristics of the application of load is applied, the application load on a member. So what will be the immediate response when you apply load, when you apply a static load over a member, over a material? So these are the two things which will happen. So these are the things we need to quantify, and that is called the stress and the strain. So as I told, the three principal ways were the tension, compression, and shear. So, in many loads. So, while in practice, we are talking about the engineering practice, the many loads were torsion. So, rather than pure shear. So, torsion plays a important role next to that tension and compression. So this is the principal ways of applying load. That the first one is the tension. You can see that the force applied, the force is pulled apart from the both sides. So the original length is that LO, and then the extended length is L. So that is after application of force. So the length is changed, or the length is increased, whereas the area. So A naught is the original area, so the area got decreased. So the same for compression, but in the reverse way. So you can see that the original area is A naught, and then the original length is L naught, and the after application of load, the length is L. So this is tension and compression. So you can see that shear and torsion also. So you can see that force, the force acting on sites, where the force were acting on the sites. So then you can see that material got deformed at an angle of theta in the case of shear load. And then you can see that in the torsion, so the T is represented as the torque. So torque will be the twisting moment at the angle of phi. So this is the torsion load. So to carry out that laboratory test, we need to have that common or a standard specimen. So to find out the properties, that is the tensile properties of any material. So from the diagram, you can see that a standard specimen of that is the ASTM standard specimen for performing tension test. So so the specimen is deformed, that is usually to fracture. So with the gradually increasing tensile load that is applied uniaxially along the long axis of a specimen. So we need to do this in a laboratory, and then in a machine, a specified machine. So we need to analyze the load applied, and then when it fracture, and then how the fracture is going on. So this is called the tension test. So this is the equipment or the apparatus used to conduct the tension test, which is called as an universal testing machine, or UTM. So there will be two. So there will be two frames, and then the top frame is a fixed one, whereas the bottom frame is a movable one, that is called as the crosshead. It will move through the screws, that is screws provided in the two columns, which can be moved by means of a hydraulic drive. And then there will be two clamps where the specimen has to be clamped together, and then an extensor meter is fitted over the workpiece, which will record the change in dimensions. So while moving the crosshead, so we are applying load to the specimen. So how much load is applied can be found from the load cell, which is mounted over the apparatus. So from that laboratory experiment, you can see that load applied and then the change in dimensions. From those data, we can find out the engineering stress and then engineering strain. You can see that from the previous diagram as I shown to you. So the engineering stress is denoted by the symbol sigma. So sigma is nothing but the ratio between the applied force and then the original cross-section area. So the unit of engineering stress is megapascal. So megapascal is 10 to the power of 6 Newton per meter square. 1 megapascal is equal to 10 to the power of 6 Newton per meter square. This one is the engineering stress. Similarly, you can find out the engineering strain. So, if that is the epsilon is equal to so Li minus Lo divided by Lo. So that is change in length. Delta L divided by Lo. Lo is nothing but the original length. So change in length and the change in dimensions along the linear axis divided by the original length is called as the engineering strain. So since both the parameters having same unit, so it got cancelled and then the engineering strain is unitless. Or somewhere, sometime you can use it as m by m or mm by m. So normally there will not be no unit for engineering strain. Next, coming to the compression test, so the test is carried out similar to the tensile test, so except that the force is compressive. You can see from the diagram, the force is compressive rather than the tensile. So the material or the specimen is contracted. The specimen is contracted along the direction of the applied stress. That is compression test. You can see that compressive force is taken to be negative because we are compressing it, so it is not extending, it is compressive, which yields a negative stress. And then, so these tests are used when the material is brittle in tension. So any material which cannot be applied a tensile test, for example, a concrete block. A concrete block cannot be tested in a tension. So there we are using the compression test to find out the compressive stress. So next is the shear test. So how the shear test is carried out? You can see that by using the same machine, that is the initial testing machine, we cannot use that what we call shear test. So for applying a test, we are going to go for a different mechanism. And then by applying the stress over the surface of the material, you can see that force acting along the three directions, that is all the directions x, y, and z. So for that, the stress is denoted by the letter tau, so which is equal to the ratio between the force and the area. So next one is the torsion test. So torsion test, as I told, it is a twisting moment, twisting force. It is a variation of shear, whereas the wherein the structural member is twisted in a manner, that is twisted for some angle phi. So that these torsional forces produce a rotational motion about a longitudinal axis of one end of the member led to the other end. That is, the other end remains stationary, remains fixed. So the one end only is twisted to some angle phi by using the torque. That is rotational motion. So these are the examples of torsion. That is, you can see that the machine axles, drive shafts, and then twist drills. So there you can see that rotary motion, the rotation motion of the shaft. Well, one end is fixed and another end is rotated. So these tests are normally performed on cylindrical solid shafts or tubes. So this is the formula. The shear stress is tau. which is a function of torque T, whereas shear strain that gamma is related to the angle of twist phi. So it's shear stress and then shear strain. So next comes the elastic deformation. So as I told, so when you apply load over a material, it got deformed. So it will change its shape from original state. That is, the deformation happens. So for most metals, so that will be elastic in nature. So the stress and strain are proposed to each other, which is called as Hooke's law. For most materials, it will be elastic in nature. While we apply load, the deformation will be elastic in nature. So this proportionality, so that is the stress and the strain were proportional to each other by some constant called as constant of proportionality, which is the unit having gigapascal, as called as the Young's modulus or the modulus of elasticity. That is capital E is equal to sigma by epsilon. So stress by strain, capital E is equal to sigma by epsilon. And then you can see that for some metal alloys, what is the modulus of elasticity in terms of Pascal, in terms of SI units, and also in terms of British units. You can see that. So of that elements of that materials or the metal alloys, you can see the lowest modulus of elasticity is magnesium. It is of 45 gigapascal, whereas the tungsten will have the highest modulus of elasticity of 407 gigapascal. And then the shear modulus and then Poisson ratio. So we'll come later for the Poisson ratio. So what is the elastic deformation? So you can see this diagram. So the diagram is for stress and strain. So the deformation in which stress and strain are proportional is called elastic deformation. You can see that straight line from the graph, the x-axis strain and then y-axis is stress. So the deformation is proportional to the stress and strain, which is called as the elastic deformation. So if you take that slope of that load applied, so then it is a modulus of elasticity, that is E, capital E. So this elastic deformation is non-permanent. So which means that when the applied tool is released, the workpiece or the material will come back to its original position. So that's why the arrow marks are shown. You can see that load applied. So load applied this direction, and then you will unload. And you release the load applied, then you will come back to its original position. That is called as elastic deformation. So here comes the Poisson ratio. So when a tensile stress is imposed on a metal specimen, an elastic elongation and accompanying strain, that is sigma in the direction of epsilon in the direction of Z, result in the direction of the applied stress. So you can see here. So this is original size, and then by application of tensile load, so what will happen? So you can see here. This is the x-axis. They taken this as x-axis, and then this one as y-axis, and this is z. So we will apply load in the direction of z. That is sigma z. That is the load is applied, stress is applied. So what will happen to the length? The change in length. You can see here. Change in length. What is the change in length? And then in this direction, change in width. What is the change in width? Like this, you can tell. That is the Poisson's ratio. So what is Poisson ratio? It is a ratio of the lateral and the axial strains. As I saw already, lateral strain to the axial strain. So for many metals and alloys, the values of Poisson ratio range between 0.25 and 0.35. So which is the ratio of linear strain, that is lateral strain and then axial strain. So then comes the plastic deformation. So earlier we saw about the elasticity. That is, when the material is subject to load, when the load is removed, the material will come back to its original position. So now comes the plastic deformation. So for most metallic materials, the elastic deformation persists only to strains of about 0.005. So behind that 0.005, there will not be any elastic deformation. So that is called as the plastic deformation. So as the material is deformed beyond this point, that is beyond the strain of about 0.005, the stress is no longer proportional to strain. So, so the deformation will be permanent and non-recoverable. So even you remove the load from the applicator, you remove the load from the material, the material will not come back to its original position or original shape. So that is called a permanent non-recoverable or plastic deformation. So from this plastic deformation, we can get the tensile properties of any material. So how these tensile properties were measured? That is, as I told already, by using the universal testing machine. So these are the tensile properties we can get from that laboratory test. So which is first one is yielding. So yielding means the stress level at which the plastic deformation begins. So you can see this from this diagram, from this graph. This is the point P. This the point is called as a proportional limit. So where the yielding starts. Up to this level, the stress will be proportional to strain. So beyond that is the proportional limit. So beyond this stress level, the stress is not proportional to strain. So the material will behave as a plastic. So, up to this one, the material will act as plastic, and then beyond this one, the material will act as up to this one, material will act as elastic. Beyond this, the material will act as a plastic. So that's what is shown in this graph. So and then the yield strength, that is another property which can be measured. The stress corresponding to the strain offset of 0.002. So the strain offset is you can see the dotted line here. So you can have that offset of strain 0.02. So regarding that yield strength, so the stress corresponding to the strain offset of 0.002. So for aluminum, so the yield strength will be of 35 megapascal. Whereas for steel, you can see that figure, so it is 1400 megapascal. That is the yield strength of two materials. So after yielding, so the stress necessary to continue this plastic deformation in metals increases to a maximum. So the material starts to yield from the proportional limit point P, and then it will go to a maximum point M. So then it decreases to a eventual fracture to point F. So that maximum point is called as the tensile strength. So it is shown in the engineering stress strain curve. We'll show later. So for that aluminum material, so the tensile strength will be of 50 megapascal. 50 megapascal, and then for the high strength steel, you can see it is 3000 megapascal. That is the tensile strength of the high strength steel. You can see here. So this one is a proportional limit. From the proportional limit, it will starts to yield. That is called as yielding, and then you can see that the yield strength. What is the yield strength? And then the yielding will continue upon the application of stress to a maximum point. That maximum point is called as the tensile strength. After that, the strain, this application of stress is going to reduce, and then the strain will reduce. So finally, the material will be fractured. You can see that specimen here. The specimen got elongated. That is the tensile yield strength, and then this is the maximum point is tensile strength. When the material starts to yield, that is starts to fracture. You can see here the cross section is changing. Finally, it will be fractured. So from that diagram, from that stress strain curve, so you can have some other properties also. So one of the properties ductility. You can see. So ductility is a measure of the degree of plastic deformation that has been sustained at fracture. So the curve under that is the stress, the area under the stress strain curve, you can see that the A to B dash, the curve, the area under the stress strain curve, we can call it as that ductile. So that is the ductility. So the material experiences very little or no plastic deformation is called as brittle. So how when it will happen, you can see here. So from this graph, so the stress will be proportional up to the limit that is called as proportional limit. So after that, a very little load it can absorb, very little load. So there will not be any plastic deformation. It will fracture. It will fracture at the application of load here itself. So then that type of materials are now called as brittle materials. So up to this strain level, so up to this stress level, the material will be fractured. That is called as brittle. Whereas up to this strain level, so the material will accept the load. So those materials are called as ductile. So the ductility can be expressed in two forms. One is percentage of elongation, that is percentage EL, or percentage of reduction in area, percentage RA. From that formula, you can see percentage of elongation is equal to the fracture length minus the original gauge length divided by original gauge length into 100 for that percentage conversion. Similarly, for percentage of reduction in area, so A naught is the original cross section area, and then AF is the cross section area at the point of fracture. So as we saw in the previous slide, the cross section of the tensile specimen will got decreased at the point of fracture. So that is the AF. So these are the two quantities you can get from the graph, that is ductility. So next one is the resilience. What is resilience? It is the capacity of a material to absorb energy when it is deformed elastically. Then upon unloading to have this energy recovered. So as I told, the energy absorbed under the curve, that is the area under the curve, or the energy absorbed up to that fracture level is called as the resilience. So what is the modulus of resilience? It is the strain energy per unit volume required to stress a material from an unloaded state up to the point of meeting. That is called as modulus of resilience, denoted by UR. So another important parameter is the toughness. So what is tough? It is a measure of the ability of material to absorb energy up to fracture. So how much energy it can absorb in terms of Joule, we can tell how much energy it can absorb until it fractures. That is called as toughness. So for dynamic loading conditions, and when a notch is present, notch toughness is assessed by using impact test. So for static loading conditions, that is denoted by the area under the curve, that is in terms of Joule, where it under a dynamic load condition, that is high strain rate, and then when a notch is present or where the stress is concentrated, we can get that notch toughness by using a impact test that we will see later. So from this we can get a property called fracture toughness, which is an indicator of the material's resistance to fracture when a crack is present. Without a crack, the material deforms. In the tensile test, there will not be any crack in the material, but even though it will deforms and then it fractured. That is static loading without presence of crack. Whereas, in the fracture toughness, we need to initiate a crack. We have to initiate a crack by using a notch. That is fracture toughness. Then comes the two stress and strain. Actually, from that engineering stress strain, that is stress strain curve, you can see that so beyond that point M, so material starts to that is absorb less load and then it start yielding. That is, the strain rate is more, but it is not true. So actually, the material is resisting the load applied, even though the cross section area has decreased. So when the during the application of load, when the load is started, when we apply load at the starting point, the cross sectional area is A. When it is yielding, the cross sectional area got decreased, and then the cross sectional area got decreasing up to that yielding point, and then to the tensile point, maximum point, and then again it starts decreasing. So whereas the load got increasing, so it is not a constant one. So what will the cross section area got decreased. So what it means is at that cross-sectional area, it is resisting the force. So that is not the true stress. Actually, what's shown there is not a true stress value. So we need to compile the true stress and strain. So that is called as the true stress, which is that is sigma t, sigma suffix t. So it's defined as the load F divided by the instantaneous cross-sectional area. So how much is the cross-sectional area at the time of application of load? So after the maximum load, what is the cross-sectional area, and then how much load is applied? That gives you the true stress. So that is the true stress developed. That is resistance offered by that material to the applied load. That is the true value. So we have to take the instantaneous cross-sectional area. That is cross-sectional area at that time of application of load. So that is sigma t, that is F divided by AI, that is instantaneous cross-sectional area. And then for that stress, we need to calculate the strain, that ET, that is epsilon t, is ln of Li by LO. LO means instantaneous cross-sectional area, and then LO is the original cross-sectional area. You can see that engineering stress and then true stress strain behavior. Actually, what is that engineering stress? So you can see this curve. So this one is proposed limit. Beyond that is the material starts yielding. So there will be yield strength. So this is the true stress value because the true stress will be more. Why? Because we need to take into account the instantaneous cross-sectional area. Because the cross-sectional area got reduced. At that cross-sectional area, it is resisting the force applied. So the stress will be more. If the cross-sectional area decreased, the stress will be more. This is the true stress curve. And then this one is engineering curve. So what we depicted earlier. So this has to be corrected to some value. So this is the corrected curve. So next is the property called hardness. So what is hardness? It is a measure of a material's resistance to localized plastic deformation. That is with a small dent or a scratch over the surface of the material, we can measure the material's resistance to localized plastic deformation. So these tests performed more frequently than any other mechanical test. So mostly widely used test is this one, hardness test, because it is very simple and inexpensive. No need of any sophisticated instruments and then equipments, and then this one is non-destructive. So whereas in tension test and compression test, after the application of load, the material got fractured. So you cannot use that specimen again. The specimen got fractured. So that is a destructive test, whereas this one is non-destructive, means we are not utilizing the material fully. So it can be used again. That is non-destructive. And then from this data hardness value, we can compute tensile strength also. From hardness, you can compute tensile strength without performing the tensile tests in the specimen. So this is the equipment used to carry out the hardness test, that is Rockwell hardness test. This is the most common method, and then we used two form of indenters. One is spherical and hardened steel balls. Another one is conical diamond. So by pressing the indenters over the surface of the material to be tested, we can find out the hardness of that material. So this hardness number, the hardness denoted in the form of number, is determined by the difference in depth of penetration resulting from the application of minor load and then later followed by a major load over the on the specimen. You can see that Rockwell hardness scales for the indenter. So imagine if the major load is 60 kilogram, then we have to go for if you use a diamond indenter, then it is denoted by symbol A, followed by that load number. And then if you use 1 by 16th inch of ball indenter, then the load is 100 kilogram. Then you have to use the symbol B. And similarly, if the load is 100 kilogram, but you are using a 1 by 8 inch of ball, 1 by 8 inch diameter of a ball intended, then you need to use the symbol E. So, for example, 8HRB. So, 8HRB means Rockwell hardness 80 on the B scale. So what is B scale? So you can see here we are using 1 by 16th inch of a ball. We are applying 100 kilogram loads. There the Rockwell hardness scale is number is 80. So that's how the tests were carried out and then the scales were utilized. The next one is the Brunel harness. So in the Brunel, this is the Brunel harness machine. You can see that the machine dial and then the point where the load is applied, the material specimen is kept. A hard spherical indenter is forced into the surface of the metal to be tested. So the diameter of the hardened steel, we are used the hardened steel or tungsten carbide diameter is 10.00 mm. We are applying load in the range of 500 and 3000 kg in 500 kg increments. Standard loads were applied. So during a test, the load is maintained constant for a specified time. So for a specified time, the load is applied that is between 10 to 30 seconds. This is a Brunel hardness test. You can see that illustrative diagram. The hardened ball is there, and then sample is kept under the indenter, and then the table you can raise or lower the table. So this Brunel hardness test is for the harder materials. Harder materials which will have greater loads. So that the Brunel hardness number is denoted by HB. So whereas Rockwell hardness is denoted by HR, it is denoted by HB. Hardness, Brunel hardness. It is a function of both the magnitude of the load and the diameter of the indentation. So the measured diameter is then converted into appropriate HP number using a chart. There will be a chart. By referring to the chart, you can conclude the hardness number of this test, Brunel hardness. So next comes the Knoop and Vickers hardness test. These were micro hardness tests. This is called as micro indentation hardness test. We are using a very small diamond indenter, which is having a pyramidal geometry. It is forced into the surface of the specimen. The loads were between 1 to 1000 grams. You can see that magnitude 1 to 1000 grams. So the resulting impression is observed under a microscope and then measured. It is converted into a hardness number. That is Knoop and Vickers micro hardness numbers. So for this Knoop and micro, so Vickers micro hardness test, a careful specimen preparation is necessary. That is, we need to grind it and polishing to a mirror finish, and then you have to carry out the test. These tests were denoted by HK and then HV. K for Knoop and then V for Vickers. And then, so these techniques were used for testing hard materials such as ceramics. Ceramic materials can be tested, were tested by this type of test only. You can see this is the different hardness testing techniques for Brunel. What is the indenter, and then what is the shape of the indenter, how it look like from the side view and then top view, a load applied, and then what is the formula to calculate that hardness. You see that Brunel hardness, and then Vickers hardness, we are using a diamond from it, and then what is the formula, and then Knoop hardness, you can use, we are using the diamond from it, and then what is the formula, and then Rockwell and the superficial Rockwell. Superficial Rockwell means the load will be increased. So that is, you can see that testing methods, various testing methods, what we discussed so far regarding hardness. And also, this is the comparison. The first one, the red color one, this one is the comparison of Mohs scale. The first scale at one is the talc, then gypsum, calcite, chlorite, and then the last, the final one, the highest one is diamond, which is the hardest material ever known by man. And then See the materials. Most plastics will be coming under this level, and then brass, and then aluminum alloys, and then common steels, alloy steels, tool steels. You can correlate the hardness of the tool steels with all the hardness scales. You can see Rockwell C scale, B scale, Brinell hardness, Knoop hardness, and then Richter hardness. This is the comparison. And the next comes the plastic deformation mechanisms. So far we discussed about some mechanical properties, how the plastic deformation mechanisms were carried out, how it is happening. So the first one is the dislocation. So why is some materials experiencing high strength, whereas some other materials were not showing strength to the applied load. So strength beyond that is up to fracture by means of some mechanisms. So, so what is that? Yeah, dislocation is a linear or one-dimensional defect around which some of the atoms are misaligned. So that is dislocation. So it's a linear or one-dimensional defect around which some of the atoms are misaligned. So these are called as linear crystalline defects. And then there are two types. One is edge dislocation, another one is screw dislocation. So the plastic deformation corresponds to the motion of a large number of dislocations. Why the plastic deformation happens? So because of the dislocations only, so the deformation happens. That is actually a defect. So due to the defect only, we are straining the material. So that is by dislocations. You can see this is the edge dislocation. So the blue dots represents the atoms, and then what will happen to the atom? The atom plane, the plane of atoms, and then what is the edge dislocation means? So this this is a lattice structure. The localized lattice distortion, that is, there will be distortion in the structure, exists along the end of an extra half plane of atoms, which also defines the dislocation line. You can see here. So so these are the group of atoms in the structure, that is in a lattice structure, whereas here in this half plane a group of atoms were missing. So this is called as the edge dislocation. So because of that, when the load is applied, so this will start to deform in that gap. It is called as edge dislocation. And the next one is the screw dislocation. So screw dislocation is resulting from the shear distortion. So shear distortion means equal and opposite forces we are applying at both sides. So the dislocation line passes through the center of the sphere or atomic plane ramp. This is the top view. You can see here. So this is the atomic lattice structure. So at one end only we are applying load. So this will start to deform. So because of that screw dislocation. So next property is the slip. So the process by which the plastic deformation is produced by dislocation motion is called as slip. The process by which the plastic deformation is produced by dislocation motion. You can see here the crystallographic plane along which the dislocation line traverses is called slip plane and the slip direction. You can see here. So this is the slip plane. This one is edge dislocation line because here the corresponding group of atoms were missing. You will see here. So, so this you can see this one, and then A. There is no pair of atoms here, and then A, B, C, D. So when you apply shear stress, so what will happen? You can see here. It will start to move. So this will start to move in this direction. So that is called as slip. So this will be corresponding to the movement of the caterpillar. That is very well example for that is caterpillar movement. So there is another deformation which is called as twinning. So this plastic deformation in some metallic materials can occur by the formation of mechanical twins. Mechanical twins means it will resemble each other. So a shear force can produce atomic displacement such that one side of plane, that is the twin boundary, atoms are located in mirror image positions of atoms on the other side. So that is called as twinning. That is twins, similar to each other. I will show you that twinning diagram. So you can see that twinning. So atom positions before twinning. You see, atoms were equally arranged at equal inter-atomic distances between them. When you apply some shear load, you can see that tau. This is a polished surface. What will happen? The atoms got displaced. So the blue circles for atom were not displaced. These blue dots, whereas the red dots were the atoms displaced from its original position. Now you can see, so this image along this line, so this is the planes. This image will be similar to the previous one. That is 10 So these are the two things deformation mechanism we saw earlier. The slip planes. This is slip by application of shear. This will deform like this. That is called a slip plane. And then this is twinning. You can see these two were, so these two will be mirror image. So that's why it is called as twins, mechanical twins, twin planes. And then comes the fracture. So what is a fracture? A simple fracture is a separation of a body into two or more pieces in response to an imposed stress that is static in nature, that is a constant one or slowly changing with time, and at temperatures that are low relative to the melting temperature of the material. This is very, very important. So we are not conducting the test at the melting point of the material. So there is no point of conduction of test at melting temperature. So the temperature, atmosphere or the temperature where the experiment is carried out is should be less than the very low. That is very low related to the melting temperature of the material. So this fracture can also occurs from fatigue. What is fatigue? When the cyclic stresses. Fatigue is repeated stress and the creep. So creep is nothing but a time-dependent deformation. Time-dependent deformation that is normally at elevated temperatures. When the temperature is more, you are applying stress repeatedly. Then deformation occurs by means of creep. When cyclic stresses are imposed, then we can get the deformation that is called as fatigue. That is failure by means of fatigue and then failure by means of creep. So that is called as fracture. That is simple fracture. So how that fracture is classified? So the fracture is classified based on the ability of a material to experience plastic deformation. So how it is deformed, how it is fractured. One is ductile, another one is brittle. So what is ductile fracture? It shows a large plastic deformation with a high energy absorption before fracture. So as we discussed in the previous slides, that is the stress strain curve, it will absorb more energy. That is, it will absorb more stress before get fractured. So then it is called as ductile fracture. Whereas brittle fracture, above beyond that proportional limit, it will absorb only very small or it will not absorb any energy before beyond that proportional limit. So then it is called as the brittle fracture. That is little or no plastic deformation with low energy absorption. It is not plastically deformed. So when it starts to move away from the elastic limit, then it will got a fracture. That is called as brittle fracture. You can see this types of fractures in a diagram illustration. See that a highly ductile fracture in which the specimen necks down. So you can see this A. It will uh, it will come to a point when it fractured. Now the fracture happens. You can see the cross section areas decrease gradually, and then it got fractured. And then this one shows the moderately ductile fracture after some necking. Some necking forms, but it is not this type of one. So after necking means reduction in the cross section area from the original area. This is the original cross section area. So this is the reduction in cross section area, and then it starts to fracture. And then you can see this one, brittle fracture, there is no plastic deformation. You can see the cross sectional area never changed. The cross-sectional area, this is the original cross-section area. This is the cross-sectional area at the time of fracture. Cross-section area at the time of fracture, cross-section, original cross-section area. There is no change in the cross-section area. Then it is called as the brittle fracture because there is no plastic deformation. Here you can see these two, this plastic deformation occurred. Then finally it got fractured. This is a partial plastic deformation, no plastic deformation at all. This one is a brittle fracture. And then you can see the images. That one is called as the very familiar cup and cone fracture of ductile fracture, cup and cone fracture of the material aluminium. You can see this resembles the shape of a cup, shape of a cone, and this one is the shape of cup and shape of a cone. It is called as cup and cone fracture. Here you can see that a very beautiful image shows you the brittle fracture. As you can see that the fractured image surfaces. No plastic deformation at all. Here you can see that plastic deformation. So the necking happens. So the material diameter got reduced and then finally it got fractured. Here the cross sectional area remains the same. So this is a brittle fracture of a grey cast iron. And then comes the fatigue. This is one type of failure mechanism, as I told already, because of the cycled stress that is repeatedly applying load. So it is a form of failure that occurs in structures subject to dynamic and fluctuating stresses. That is, it is not continuous in nature, but it will fluctuate, and then it is dynamic. It can happen at any time and for a long number of long duration or a very small duration. So, for example, you can take that bridges, aircrafts, and then machine components. So, while the bridges, in bridges, you can see that whenever the traffic is there, when the vehicle moves over the bridge, then only the load will act. Otherwise, the no load act on the bridge. Similarly, aircraft, when it is flying, then only the load is acting on the wings. Otherwise, it won't. And then similarly, the machine components, whenever the machine components were kept in use, the load will act on the component. So this term fatigue is used because this type of failure normally occurs after a lengthy period of repeated stress or strain cycling. After a long time only you can get that stress. It is important as much as it is the single largest case of failure in metals. So estimated to involve in approximately 90% of metallic failures. That is, of the failure of machine components or any material structures used, the failure is failure mode. The reason for failure is fatigue mostly. That is 90% of failure is due to the fatigue failure mechanisms. So that polymers and ceramics, except for glass in that ceramics, are also susceptible to this type of failure. Even the polymers also fail. So the polymers having a very good tensile strength, but these polymers will also fail according to this fatigue. So the fatigue is catastrophic and insidious, occurring very suddenly and without warning. It will not get any warning. That is, it will not show any signs of failure. So it is brittle-like in nature, even in normal ductile metals. So with the previous slides, we saw that the cup and cone fracture. So when it is fatigue, when you are applying load repeatedly for continuous duration, then it will not experience like a ductile material. So it is not. It will not behave like ductile material. It will react. It will show failure similar to brittle materials due to application of load continuously. So how this fatigue happens? This occurs by the initiation and propagation of cracks, and typically this fracture surface is perpendicular to the direction of an applied tensile stress. So how it happens? Because of the application of load, the cracks will be initiated in the specimen, and then those cracks will be propagated, and then finally it got fractured. That is fatigue. This fatigue test can be done. So the values of fatigue, how when a material will be got failure because of the fatigue. can be predicted by using that test called fatigue test. You can see here both tension and compression in the and also rotational motion. We are imposing tension and then compression. So on the top we will have to get that compression, at the bottom we will get that tension, and also it got rotating. And then at the same time you are applying load. You can see here. So at the same time you are applying load. So all the loads were acting. All the forces were acting over the specimen for a set of time, and then you can find out that fatigue value. That is number of cycles. How many cycles you are applying load? We can find out that. So this is the specimen similar to the tensile test that is kept in the test specimen, and they will get the values. That is number of cycles. So that the number of cycles, actually that stress amplitude, the number of cycles, how many cycles the material experiences is depicted as S, and then so the number of cycles to failure, that is in terms of N. So that is called as SN curve. So you got to follow an SN curve, plot an SN curve for the values of S and the number of cycles to failure in the logarithmic scale. From this XN curve, we can ascertain the fatigue limit. And then this is another one you can see here. So we can find out the fatigue strength. Fatigue strength at the N1 cycles, and then you can see that the fatigue life. So these are the parameters you can get from this SN curve. So fatigue limit, fatigue strength, and then fatigue life you can get. So as I told, so what is that fatigue limit? That is which the other is called as endurance limit. The limiting stress level below which the fatigue failure will not occur. So if you apply load beyond this, that is up to this level, the fatigue will not occur. That is failure due to fatigue will not occur, which is called as the endurance limit. So when the load applied for that number of cycles is beyond this limit, which is called as endurance limit, the material will fail due to that fatigue. And then fatigue strength, which is defined as the stress level at which failure will occur for some specified number of cycles. That is, if it is 10 power 7 cycles, then beyond the 10 power 7 cycles, suppose 10 power 8 cycle, then material will fail. That is fatigue strength. So material will hold good for that load for up to 10 power 7 cycles. Then it is the fatigue strength of that material. And then what is the fatigue life? It is a number of cycles to cause failure at specified stress levels. So suppose if it is 10 power 7 cycles, then that material will hold good for 10 power 7 cycles. That is called as the fatigue life. So beyond that, the material will got failure. That is or fracture. So it is called as fatigue life. So you can see that the process of fatigue failure. So the crack will be nucleated first. So this is the cross section area. You can see cross section area. The crack will be nucleated first here. You can see here in the side view, and then the crack got it grows due to application of load. You see here the crack grows. The crack grows here. Finally, the crack extend up to the entire cross section, and then it got failure. So this is the three stages: crack initiation, and then our crack nucleation, crack growth, and then fracture. These are the three stages. And then next comes the creep. So the creep is the time-dependent plastic deformation of material subject to a constant load or stress at temperatures greater than about zero point 0.4 of the melting point of that material. So that's time-dependent plastic deformation. You are applying a constant load. The temperature is more than zero point 0.4 of the melting point of the respective material. So, for example, the turbine rotors in jet engines, aircraft jet engines, and steam generators that experience centrifugal stress and high pressure streamlines. You can see the turbine rotors will have that high temperature because of the exhaust gases coming out of the aircraft engine. So that will experience creep. So because the load acts on it, and also the temperature is very high. So there you can see that failure due to creep. So the amorphous polymers and then the rubbers also very sensitive to the deformation, that is creep deformation. So the creep test is carried out, subjecting a specimen to a constant load of stress while maintaining a constant temperature, and then a deformation or strain is measured and plotted as a function of elapsed time. That is, we will call it as a creep curve, a generalized creep curve. Constant stress tests are employed and to provide better understanding of the mechanism of creep by using that material test specimen. You can see here. So this is the creep curve. Well, from the data we got, we have to plot against the time and then strain. The creep strain, and then here it is time. So how the material got fracture or rupture. So upon application of the load, there is an instantaneous deformation, which is mostly elastic, that is at the early stages. So then the material starts to deform. Finally, it will got rupture. There are three stages. The first stage, this is instantaneous deformation, and then next it will start to elongate. It will deform. At some point, the deformation is constant, and then again the deformation is increased. Finally, it got ruptured. So there are three stages. The one is called as the primary stage or transient creep, and then second one is secondary stage or steady state creep, since the strain is constant, and then the last one is tertiary creep. This one you see the time t as an y-axis, sorry, x-axis, creep strain. Data obtained from the material testing the specimen. This is the instantaneous deformation. Later application of load, it will start to deform. This one is primary creep, and then after this, the deformation is proportional. So this is secondary creep. Therefore, deformation is constant. Then the deformation is increasing. This is tertiary creep. Finally, at the end of the tertiary creep, the material got ruptured or fractured. So this is the primary creep. It occurs first, and then it is constantly decreasing creep rate. The creep rate is constantly decreasing. You can see here, constantly decreasing creep rate. You can see this one is increasing, but it is constantly, the creep rate is decreasing. Whereas the time is increasing here, the creep strain is increasing here, but the creep rate is decreasing per time. The material is experiencing an increase in creep resistance. This is called as a primary creep. Next one, secondary creep, you can see the creep rate is constant. Here the creep rate is constant. The time is increasing, at the same time the strain is also increasing. So the creep rate is constant, and then the plot becomes linear. It will be like a straight line. So this is mostly this creep is the longest duration. The secondary creep occurs for some more time. So that is the stage of longest duration, the secondary creep. So finally, there is a tertiary creep here. There is an acceleration of the rate and ultimate failure. So what you can see here, sudden acceleration. So the strain got increased, and finally it got a failure in the form of rupture. This failure is termed as rupture. So in the fatigue we call it as a fracture, whereas in the creep we termed it as rupture. So this results from the microstructural or metallurgical changes happening inside the specimen. So the specimen got ruptured. And then next comes the impact fracture testing. So, so impact test conditions were chosen to represent the most severe relative to the potential for fracture. So impact, so it is very instantaneous in nature, and then it is very severe also. So how it happens? So that is deformation at a relatively low temperature, and then a high strain rate, and then a triaxial state of stress is present. These were the two conditions where the impact fracture will happen. So for that we have to carry out that impact fracture test. So there are some two standard tests available. One is CHARP impact test, and then IZOD impact test, which is used to measure the impact energy. Sometimes they are also called as notch toughness because you are creating a notch on the specimen before carrying out the test. So this notch, SARP V notch, CVN, so is the most commonly used in the United States, and then IZOD we are also using sometimes. So this is the specimen used for impact testing. You can see that specimen. So the dimensions were 10 mm, 10 by 10, and then length is according to the load applied. Mostly it is 50 mm in length, and then 10 mm in width and 10 mm in breadth. And then at the center we need to create a notch. We need to machine a notch here at 8 mm from the bottom at the center, square bar. So this is the apparatus or notch fracture toughness testing machine, which is called as IZOD or CHARP. There will be a scale over there, and then pointer, and then a hanging pendulum with some hammer, and then a place where the specimen has to kept here. So anvil at a height of h, and then this where the hammer has to lifted to some height, and then it is made to free fall over the specimen. The hammer will hit the specimen, and then it will break. So what is the energy it absorbed at the time of breaking will be denoted here in the scale. And this is how the impact test works. The load is applied as an impact blow from the pendulum, and then the specimen, as I told, the specimen is positioned at the base. So this knife edge pendulum strikes and fractures the specimen. So the notch will be acting as a stress concentration. So immediately the specimen will cut fracture. So as I told, this one we have to swing it, that is raise the height of the pendulum, and the energy will be absorbed. Is a measure of that difference between H and H bar in that, as I shown in the previous slide. So the primary difference between the CHARP and IZOD is the specimen, placing of specimen, how the specimen is placed on the anvil. You can see here for IZOD, the notch will be facing the pendulum. You can see here, this is the pendulum. The notch is kept, the workpiece is kept in the upright position. The notch is facing the pendulum. This one is now IZOD test. Whereas in CHARP, so the workpiece is kept in a horizontal position, and then the notch will be in the opposite position. So that the function, that is why you are carrying out that CHARP and IZA test, we need to know about the toughness, that is how much energy is absorbed before fracture. So it is also used to determine whether or not a material experience a ductile to brittle transition without with decrease in temperature, and if so, the range of temperature over which it occurs. So this can be also used to calculate this one. It is called as DBT, DBTT, ductile to brittle transition temperature. So it related to the temperature dependence of the impact energy, whether temperature affects the impact energy of the material or not. You can see here. So ductile to brittle transition. This is the impact energy calculated in terms of joules, and then temperature. You can see it is 0 degree. It is 2040 room temperature here. What will happen if the temperature is got reduced? The impact energy got reduced. So and then here you see that if the temperature is increased, the impact energy got increased. That means the temperature decreases the impact energy, and also you can see that the shear fracture in terms of shear fracture you can see here. So this shows the impact energy. This one is room temperature. So if we carry out test at below the room temperature, the impact energy got reduced. The energy absorbed by the specimen will be very low. So what it implies is that below the room temperature or the sub-zero temperature, it will not absorb more energy. It will fail very quickly. So that high temperature, the CV energy is relatively large in correlation with the ductile mode of fracture. As I told, as the temperature is lowered, the impact energy drops suddenly. So that is the fracture. The mode of fracture is brittle. It will show a brittle mode of fracture. You can see this appearance of fracture failure surface. You can see this one 79 degrees Celsius and then 24 degrees Celsius, 16 degree, 4 degree, minus 12 degrees Celsius and minus 59 degrees Celsius. So at 79 degrees Celsius, so this appears as ductile fracture, the original fracture surface of IZOD. Whereas you can see the totally brittle surface, that is, the surface will be granular or shiny in nature. It is at the minus 59. You can see the difference in surface. This one is dull, whereas you can see the surfaces are shiny or polished. So, minus 12, minus 4, and then minus 12, 4, and then 16. You can see mixture of those two failure mechanisms. So this is how the ductile to brittle transition occurs. So at 79 degree, the fracture is ductile in nature, whereas at minus 59, the fracture is brittle in nature. That is called as ductile to brittle transition temperature. So, so that's all about our lecture. We discussed about all the modes of fracture, the failure mechanisms, ductile and fatigue and creep, and then we discussed about the mechanical properties, and then the tension, compression, and the hardness test, and then the dislocation, slip, and tuning mechanisms. So that's all about the unit 5. Thank you so much.